Hello everyone. In this module, I will discuss ADC, that is analog to digital converter. As we all know, the microcontroller require digital input to it, and then it can later on process. But if we have to interface our controller with something which will produce the analog output, in this situation, we do require in between the ADC, that is, which will convert the analog signal to digital signal, which later on can be fed in to the microcontroller for processing further. So every microcontroller require one peripheral, which is the digital converter, analog to digital converter, for processing the analog signals. For example, our controller can be interfaced with the temperature sensor, and the temperature sensor can sense the temperature and produce the analog signal out of it. But our controller can only understand the digital input. In this situation, initially, whatever the sensor, the temperature sensor would produce, will first go to the analog to digital converter module. That module will further convert it into the digital signal. That digital signal will be feeding to our microcontroller. So in these situations, we do require analog to digital converter, and that's why uh, this is important peripheral. Now we will understand that how we will interface our ADC module with our core LPC1768. So on our kit, two ADC modules are available, AD04 and AD05. In total, 8 ADC modules are possible, but depending on the size, only 2 are possible in our kit. But in reality, 8 possible modules are there, and the module means those are the 8 channels over which uh, analog input can be fed in, and this is internally connected to our board. And so whatever we will feed in will get converted to the digital output and will be feed in to our LPC1768, and later on we can display it to over 7 segment, we can display it over LCD, or in whatever way we want to use that converted output, the digital output, we can use it. So we will concern here only about AD04 and AD05. In general, means in total 8 ADC modules are available: AD0.0, AD0.1 till 7. So in our kit, AD04 and AD05 are available. Now we will talk about the schematic which is given here. Here, this P1.31, this is the port and the pin number is 31. So port number 1, pin number 31 is associated with AD05. So this is the AD05 is associated with the pin number 31 of port number 1. So this is connected to port number 131. So this is AD05, which is connected to port number 1 and number 31. And this is the reference voltage. We will later on come to know that what is the importance of reference voltage. And the reference voltage in LPC 1768 is 3.3 volt. It is not 5 volt. 5 is the VCC voltage. 5 is VCC voltage for operating the overall microcontroller, but our controller pins, so they can withstand the maximum of 3.3 voltage. and this is the LCD. So the idea here is whatever the input we will get over the pin 1.31, that we will later on display over the LCD. So these are our LCDs here working in 4-bit mode. So pin number 4, 8, 9, and 10. So of port number 1, pin number 4, 8, 9, and 10, these pins are connected to 11, 12, 13, and 14. So means data line D4, D5, D6, and D7. So these are the data lines connected to pin number 11, 12, 13, and 14. We are here working in 4-bit mode, and this is for reset purpose. I think not reset, RS, register select. On the 4th pin, we are connecting port number 2, pin number 0. That is for register select. If the 0 would be there, the command, and 1 would be there, and the data. And 5th one is for read and write. So for writing purpose and the reading purpose will be decided by the port number 2, pin number 1, and port number 2 and pin number 2 is for enabling purpose. In the separate module where I will discuss the LCD in detail, will go in detail about the pin and the pin configurations and their importance. But here the idea of this schematic is that port number 1, pin number 31 is associated with the ADC module for 5, means the channel 5. So whatever be the input over that input we want to send through these 4 data lines, and we will manage the command and the data, means in short, we will control LCD using these 3 lines: RS, enable, and read write. So that is LCD. So here we are using 16 cross 2 LCD. That means 16 character in one line, and there are 2 lines. In 4-bit mode we will use. So this is all about the schematic. And already I've disclosed about the availability of ADC pins. So we have AD04 and 5 channel. Only these 2 channels are available. So 2 input analog signals can be fed in to these available channels. Now, as with every peripheral, there are certain associated registers through which we can control, we can monitor, we can regulate the concerned peripheral module. So here, first we will understand that if we have to configure certain pin as ADC pins, because 7 available channels are there, and these 7 available channels require the corresponding pin over which we can feed in the digital input, whatever be the converted digital input. So we require means 8 pins. In total, 8 channels are available. So for that, we have to configure it through pin select register. In general, if you will not configure it, most of the pins are GPIO pins, but we don't want to operate on GPIO configuration. We want to change the configuration from GPIO to ADC configuration. So for that purpose, 8 in total channels are available. We require 8 corresponding pin. Now we will see that what and all pins are available for configuring them as ADC pin, and what is the function select for that in the pin select register. So we'll go to here. So for ADC 0, for the channel 0, port and pin which is available for configuration is port number 0, pin number 23rd, and the function is 1. So if we have to configure the port number 0, pin number 23rd as AD0, so we have to write over the 14th and the 15th bit of the pin select register 01. Then after configuring it in this way, No more AD0 will be GPIO pin, then AD0 will means port number 0, pin number 23 will start functioning as ADC pin. Then controller would acknowledge that pin as ADC pin. So whatever comes over that, our LPC would consider that as the digital converted output. And AD0, AD1, so for that the port number 0, pin number 24. Likewise for AD2, port number 0, pin number 25, and the function is still 1. The function is still 1. And AD3 also function is 126, AD4 pin number 1, pin number 4, port number 1, pin number 30, AD5 pin number, port number 1, pin number 31. But here there is a one change. Now the function is no more 1. The function number is 3 now. So 28th and 29th bit of the pin select should have the value 1 1 instead of 0 1, as in the case till AD3. Likewise for AD5 the function is 3. So 30 and 31 bit in the pin select 3 register should be 1 1. Likewise AD6 the function is 2. That means 6th and 7th bit of the pin select 0 should be 1 0. Likewise for AD7 the function is 2nd. So 4th and 5th bit of the pin select register should be 1 0. So that's all about configuring the pin corresponding to ADC functionality. In this way, through properly using and utilizing the concerned bit in the pin select register, we can configure the pins, the corresponding port pins as ADC pins instead of GPIO. So here, in this example, our idea is to make and configure the port number 1 and its pin number 31. So port number 1, pin number 31 as AD5. So in this situation, what we do need to here do is 30 and 31st bit should have the value 3. That means 1 1. So exactly the same thing we are doing here. Pin select 3. On the 30th bit we are writing 0 1, and on the 31st bit then once again we are writing 1. So 30 and 31 will become 1 1. In one line also we can do the same thing. That's all totally depend on you how you will end up doing it. The idea is 30 and 30 bit should be 1 1 in pin select 3 register. So in pin select 3 register, 30 and 31 bit should be 1. So irrespective of how you will do it, the end result should be that 30 and 31st bit should be 1 1. Then that will configure our port number 1, pin number 31 as AD5. That's all about configuration. Once we have configured it, now I will talk a little bit about powering up the ADC module, because all the peripherals which are associated with our core, they need to be powered up. If you will not power up, then there will be no proper connection. So for that purpose, there is one P configuration register, and its corresponding bit should be set as 1. Now we will go to the P configuration register and see which bit in the P configuration register should be 1 for powering up the ADC module. So this is our power configuration register. This is power configuration register that comes under LPC underscore system configuration. So that comes under LPC underscore system configuration. So it is not only just be required to configure power for ADC. The maximum possible modules which can be interfaced with the LPC1768 to power up any one of the device, any one of the peripheral. We do need this power configuration register. So in this power configuration register, first the 0th bit is for no use, it is reserved. Then already we have discussed about the timers. So for powering up timer 0, we need to set the bit 1 as 1. So for configuring the power for power PC timer 0, we need to make the bit 1 as 1. Likewise, second bit is for timer 1, and this is for UART 0. Fourth one is for UART 1. Sixth one is for pulse width modulation 1. Likewise, seventh is for I2C. And this is the 12th bit. So in our situation, corresponding to ADC, we need to make the bit 12th as 1 for powering up the ADC module. Likewise, if you have to power up any one of the device, it's always advised to look the power configuration register and consult the power configuration register and set the corresponding bit as 1 that will power up the device, that will own the device over the kit, and then the connections would be proper. That is all about configuring the power. Now, any peripheral, whenever gets interfaced with the main core, so core has its clock that is called main clock, and now peripheral also need one clock to sync with the main clock. So peripheral clock, we talk about the peripheral clock in that situation, in that scenario. So peripheral clock also get its means clock frequency from the main clock. So peripheral clock in a way is dependent on the main clock. So there is only one main clock. All the peripherals will sync their peripheral clock with the main clock. So for that purpose, in what order will they sync it? Because peripherals are not as fast as the main clock, as the main device. So main device clock works on the higher frequency, but peripheral device can't work on the greater frequency and the higher frequency. So in that situation, they have to slightly adjust their clock. How to then adjust it and then how to configure this adjustment, for that purpose also there is PCLK select registers. And there are 4 options. Either the peripheral clock can be equal to the core clock, or peripheral clock can be just the half of the core clock, or the quarter of the core clock, or by 1/8 of the core clock. So to select any one of the option, we need to configure that selection through the proper use of the pin select registers. So not pin select, PCLK select registers. So there are 2 PCLK select registers, PCLK select register 0, PCLK select register 1. So we will see now, because this is also one module, peripheral module, it also need to select its peripheral clock in relation to the core clock. So these are all the 4 options. So 00 is for peripheral clock is equal to core clock by 4. 01 is for peripheral clock is equal to core clock, and this is by default. If the value is 00, obviously in the PCLK select register the value is 00. If you haven't written anything, so by default the value will remain be 00. So this is the by default value. This is the by default configuration. And 10 is for just the half of the core clock. 11 is by 8 of the core clock. Now in this PCLK select 1 register, so the select 0 register, sorry, PCLK select 0 register. So for timer 0, second and third, so because every peripheral require 2 bits, because any one of these 4 options it has to select from. So to select any one of these 4 options, it requires 2 bits, because 4 possibilities are there. And to summarize, digitally summarize those 4 possibilities, you require 2 bits. So for timer 0, peripheral module, second and third bit uh, would be used. For timer 1, fourth and fifth bit would be used. Sixth and seventh would be for UART0, eighth and ninth would be for UART1. Likewise, for our ADC, 24th and 25th bit. 24th and 25th bit will be used, PCLK ADC. So if you will write here instead of 00 any other value corresponding to that, peripheral clock will be adjusted in relation with the core clock. So if we write over the bit 24th and 25th 1 1, in that situation 1 1 means peripheral clock will be by 8th of the core clock. If we will write 1 0, then peripheral clock will be just half of the core clock. So in this way we can adjust, but in our program, as in the next lecture I will discuss some programs related to ADC also. So in our kit, everything is well adjusted. We don't need to adjust our core clock. But even if you want to adjust, you can adjust is using the PCLK select register 0. So 24th and 25th bit. So this register, PCLK select register 0, PCLK select register 1, these are 2 registers which are used for selecting the peripheral clock in relation with the core clock. For the maximum, I think the all possible peripherals which can be interfaced with the core. Now, or till now, we have seen how to configure the pins, which may later on start working as ADC pin. How to power up the modules. For that purpose, we require pin configuration register. That's the part of LPC underscore system configuration. And finally, we discussed about the peripheral clock selection in relation with the core clock using PCLK select 0 register or PCLK select 1 register. In power configuration register, we require only single bit. So just the selection of one single bit, power up the device, setting up the single bit. In power PCLK selection register for selecting the peripheral clock, we require 2 bits for each and every peripheral, because there are 4 possibilities. So that is all about the background which you do need require for understanding the ADC working. Now in the next phase, we will understand how our ADC module, that is analog to digital converter, works. Actually, our ADC module, all these channels are multiplexed with 12-bit approximate register, 12-bit successive approximate register. So at a time, because 8 input possibilities are there, so at a time in parallel also, 8 analog inputs can be fed into the 8 channels, but there is only one approximation register. And so we have to, even in a situation where in parallel also we have to convert all the possible feed-in analog signals. So that also will happen in round robin way. That mode of operation is called burst mode of operation, and there is another mode of operation that is called software control mode. In software control mode, only one input signal would be there. So out of 8 at a time, only one we would use, and that one would go to feed into the ADC module, and we'll get the converted result. But in case of the burst mode, parallelly there may be several analog inputs which need to be converted at a time. But at a time, because there is only one multiplexed register, so all the things would go in round robin way. So first, like suppose if AD01 till AD07, AD01 to AD07, that means seven input signals are there. So in round robin way, they will be passed or they will be converted using the ADC module, and their approximate converted value will find its position in one register, that is a successive approximate register. Here in LPC 1768, we are using 12-bit approximation algorithm. So our SA successive approximate register comprises of 12-bit. So anything which we are feeding in as analog signal will find its expression, the converted expression, in 12-bit digital output. That 12-bit digital output later on we would convert into its approximate equivalent voltage value. One more important thing which I want to mention here, ADC always require voltage in input. It may be possible because as I gave the example of temperature sensor, so it may be any other analog sensor which will not produce output in voltage. But if we will pass it through the ADC, then we have to first convert that analog value, which is not in voltage, into its approximate voltage in some way. In some proportion, we have to convert it into its equivalent analog voltage, and that analog voltage should feed into any one of these ADC channels. Then it will convert it into its equivalent digital 12-bit approximate digital value. That digital value then further need to be processed. That we will see that how we will process it. That is simple proportion. Uh, uh, in the subsequent phase, we will understand the conversion of that digital into its equivalent later on digital voltage value. So this is about the theoretical aspect pertaining to the ADC module. Now we will understand the registers involved with ADC module. These registers are helpful in monitoring, controlling the ADC module, and then later on, whatever be the converted value, figuring out whether the conversion has happened and what is the converted value, and all these things we can monitor and control using these register sets. So in total, 1, 2, 3, 4, and 5. So 5 types of registers do exist for controlling and monitoring the ADC module. First is for configuring and controlling ADC module, that is ADCR. So it is used for configuring the ADC. Configuring in the sense we can see this is the ADC. So obviously when we are talking about the register, in total 32 bits are there. So initial out of those 32 bits, so initial 8 bits we will use to select the channel. In total, 8 channels exist. So out of those 8 channels, over which channel we are expecting the input. So that all input channel should be selected here. So suppose if we are selecting 4th and 5th channel where we are expecting analog input. So we have to here configure using ADCR register the selection bits corresponding to 4th and 5th channel. So 4th and 5th bit should be 1. Then 8 to 50, this is for clock division. So this is in relation with the peripheral clock. Already we have seen the selection of the peripheral clock in relation with the core clock using PCLK select 0 register, where 24th and 25th bit were the deciding factor that what would be the relation between peripheral clock and the core clock. Now, suppose whatever, because there are only the division, only four possibilities were there. Either the peripheral clock could be equal to the core clock, or maybe half of the core clock, maybe quarter of the core clock, or by eighth of the core clock. But if suppose we want to even divide to not in this ratio, in some other ratio, or further we want to divide our peripheral clock in relation with the core clock. So whatever we will write here from 8 to 15. So then this thing plus 1, that number will divide. So whatever we ever selected peripheral clock, so then the new peripheral clock would be equal to whatever we have selected using PCLK select register 0 divided by CLCK division plus 1. So suppose if the value written over 8 to 15 is 1, that means 1 plus 1 is 2. And already we have selected the PCLK and the relationship was 1 1. So that means PCLK is equal to core clock divided by 8. So already using PCLK select register 0, we have selected it. Now we want to further divide it. Now for further division, we have written here one value from 8 to 15, the value is 1. Then 1 plus 1 is 2. So the new peripheral clock would be is equal to the old peripheral clock. The old peripheral clock was CCLK divided by 8. CCLK divided by 8, then that is multiplied by 1 by 2. Then so 8 multiplied by 2, 16. So then the resultant peripheral clock would be equal to 1 by 16 instead of 1 by 8. So if further division in any way you want to do, that thing we can manage using the value written over 8 to 15. So whatever with the value we are expecting, and that is not possible through those four options, then the value of our choice, accordingly we can write the value in the clock division, and further also we can divide the resultant peripheral clock. Now, as I have already disclosed, that there are two possibilities in which our ADC module can work. One is software controlled, another is burst mode, software controlled way and the burst controlled way. In software controlled way, only one input we can feed in. So in that situation, out of these selection bits, only one should be 1. Only one bit should have the value 1. So if 16 bit is 0, that means we are going for software controlled mode. In that situation, it would not be possible for us to write 2 ones from the position 0 to 7. So only one should be selected, because in software control mode, only one input will be converted into its equivalent digital output. Whereas in case of the burst mode, more than one inputs can be fed in. Then our ADC module will take them one by one in round robin fashion and convert and write those values the 12-bit values in the successive approximation register. That all we will see later on, where it will write the value. So for that to select, the first mode to select, we have to make the 16th bit as 1. Then from 17 to 20, these are reserved for no use. Already we have seen how to power up the ADC module uh, by setting up the 12th bit in the power configuration register. There is one more check that once initially we have to do it, then there is one more possibility, not possibility, it's a further check or a further switch after switching on through power configuration register. There is one more switch that is in ADCR register. So 21st bit also should be one to power up the device, the power up the modules, the ADC module. So this is the power down bit. So generally it is 0. If it is 0, then there would be no conversion. The moment you will make it 1, then it will select the input and will start taking the feed in from the input channels. Then from 22nd to 23rd, these are reserved bit. These 2 bits are reserved. 24 to 24, 25, and 26. These 3 bits are start bit. Start means if you will write 000 over the start, it will not start the conversion. If we will write 001, that means 001 value, then it will start converting uh, the analog input into its digital equivalent output. In between, because 3 bits, 8 possibilities are there. So with software controlled mode, so if we are not operating in the burst mode, in that situation, the value over here, 26 to 20, 24 to 26, should be 001. And you should start it. You should start the conversion. And 000 is for not starting the conversion. But if we are using the burst mode, in that situation, the value over 24 to 26 should be 000, because in that situation, ADC module internally will manage when to start and when to stop, because there are several input signals which it has to convert. So it will decide on its own internally when to start, which signal to take in, and then which signal to then stop, and so ADC module will do it on its own internally. Whereas in case of the software control mode, 000 means no starting. There is no, we haven't started it. 001 will start it. But suppose if we want to start it over the edge, the rising edge or the falling edge, in that situation, 27th bit should be 1, and only in the situation where 27th bit is 1, then other possibilities are possible. Other 6 possibilities are possible. 3 for the rising edge, the position it will mention that over the rising edge. So 3 or over the 3 positions, it can start converting the input signal. Likewise, 3 more possibilities are for the falling edge, where it can start converting the input signal into its digital equivalent outputs. So that is all about the ADCR, the configuration register. Once again, in brief, for the selection bits, the 8 selection bits is to select the input signals over which ADC module will finally start working and convert the analog signal to the digital signal. Further division, if we are expecting the further division, our requirement is to further slow down our peripheral clock, because using PCLK select register, only 4 possibilities are there, and we want to further decrease the frequency. In that situation, we can write some values, or whatever we will write +1 will go as a multiplier factor and whatever we were previous selected the PCLK, then in that proportion we can slow it down. If we want to uh, work in burst mode, then 16 bit should be 1. Power up for powering up the device, 21st bit should be 1. And if we are using the software controlled mode, then the value should be 001. If we are using the edge over the edge, we want to start our conversion rising edge or the falling edge, then the edge should be 1, and then the values apart from 00001, all other 6 values would be the possibilities here over the bit 24 to 26. So that is all about the ADC configuration register. So through configuration, actually we are selecting the mode, either the software controlled mode or the burst mode we are selecting. We are powering up the device. We are selecting the input signals. We are monitoring or adjusting our peripheral clock. And we are setting up the start time. So when to start, or either at the edges or at the level. So that's all about the configuration register. Now we will move to the global data register. So just after conversion, obviously we require some register where our module will write the output. So this is the global data register, because in global data register, whatever be the recently converted value, so that recently converted digital value will find the place here in the analog ADC global data register. 0 to 3, those are reserved. And as I have already disclosed that we are using here 12-bit successive approximation method for converting our analog signal to digital signal. So the digital signal would be of 12-bit size. So those 12 bits we will write here in the global data register from 4th position till 15th bit position. Then 16th to 23rd are of no use. 24th and 26th, because it's a global data registers, and it will hold the converted, recently converted digital value. So then we should also know that this converted value corresponds to which input channel. 8 channels are possible, so to depict 8 channels we require at least 3 bits. So for that purpose, this is the channel bits 24th to 26. Then 27th bit. So 27th bit is for overrun. Before overrun, we will understand the bit number 31st. 31st, the last bit position, the maximum significant bit, MSV bit. 31st, that's the done bit. When the conversion will take place and over, then in that situation, 31st bit to ADC module will make as 1. So that's the done bit that confirm that conversion has taken place. Now, what about the overrun? So 27 bit is overrun bit. Overrun bit corresponds to, this bit is set during the burst mode first, where the previous conversion data is overwritten by the new conversion data. And there is one more catch here. So here we are overwriting the value, but in a situation where already this register has been read in the previous cycle before being overridden. In that situation, overrun bit would not be 1. Overrun bit would only be 1 in a situation when in the next cycle ADC module is overwriting the result value from 4 to 15, and along with this, in the previous cycle nobody has read the written value in the previous cycle. So in the previous converted cycle, nobody has read that value till now. And before reading only, in the next cycle, ADC module has once again rewritten the value over 4 to 15 bit. In that situation, overrun bit would be 1, and that only happens during the burst mode, because in software control mode there is only one channel, and that only we are converting it to only once. We are not even repeating it. There is no point of repeating that conversion. So only once we are converting it, so there is no chance of overwriting it. So only in the burst mode overwriting is possible, and that too if in the previous cycle whatever be the value written not being met by anyone. In that situation, overrun bit would be 1. Exactly, because 8 channels are there, so corresponding to 8 channel, then we have 8 data registers, and those data registers are here ADDR0 to ADDR7. There is only one change, or otherwise more or less global data register and ADDR register structure is same, because ADDR registers doesn't require the channel number, so that bit is reserved. So here uh, 80 24 to 26 bit, that is also reserved. Apart from that, the structure is exactly same. 0 to 3 it is reserved for ADDR register. 4 to 15 will hold the converted value. Then 16 to 26 it is reserved. 27 is overrun bit, and 31 is done bit. So that is all about the registers. This register. Then there is one more register, an ADC status register. This status register will hold the memory image of done bit and overrun bit. So how many done bits are there? In total, 8 channels are possible, corresponding to eight data registers are there. In eight data registers, we have 31st bit. 31st bit as the done bit. So in status register from 0 to 7, from 0 to 7, that is nothing but just the memory image of that bit position. So that's just the mirror image of that bit position. Likewise, from 8 to 15, the next 8 to 15 is the mirror image of the bit position corresponding to overrun in the respective data registers. So 8 overrun, 8 done bits, and then the 16th bit is for interrupt. Because in burst mode, there is a high chance of overwriting. So in that situation, how to manage it? Through interrupt, it could be managed. Once any conversion happen and the done bit is 1, we can associate that done bit with interrupt. So for that purpose, AD interrupt. So in the AD interrupt register, AD interrupt enable register. So 8 bits are there. Each 8 bit is corresponding to the corresponding done bit. The moment that done bit will become 1, it will trigger the interrupt, and then through the interrupt handler we can handle the corresponding conversion. So that is all about the status register, AD status register, and this is the software control mode. In software control mode, only one conversion will happen at a time, whereas in hardware or the burst mode, more than one conversions are possible. And when more than one conversions are possible, we require round robin way, because all the channels are multiplexed with only 12 bits of successive approximation register. That is only one module of conversion, and that's why in round robin way our ADC module can handle all the parallel inputs, parallel analog inputs, and in that situation overwriting may be the possibility. How to handle the overwriting possibility we can handle is through interrupt. So in burst mode we can input use of the interrupt. So for that purpose, analog to digital interrupt enable register is there, in which the initial 8 bits corresponding to the corresponding done bit. So the done bit is 1, those are all associated. If you will, then it will trigger the interrupt, and through interrupt handler we can handle the converted value. So that is all about the ADC module, its register structure. Now in the next phase, I will discuss finally how the conversion will happen. How finally the analog input which will go through uh, the channels, the input channels, how it will be converted into its equivalent 12-bit successive approximate value. For that purpose, there is one successive approximation algorithm. We'll understand the successive approximation algorithm. And here is the successive approximation algorithm. So here I will make you understand the successive approximation algorithm through 4-bit successive approximation algorithm. In LPC 1768, the successive approximation algorithm will require 12-bit. So it's a 12-bit successive approximation algorithm which we are using with our core LPC 1768. For understanding purpose, here we are understanding it through 4-bit successive approximation algorithm, 4-bit. So the resultant final digital output will get in 4 bits. For that purpose, first, any successive approximation algorithm require reference voltage. In case of LPC 1768, the reference voltage is 3.3 volt. Whereas in this example, the reference voltage is 16 volt. This is the reference voltage. And there's the positive reference and the negative reference is 0 voltage. So we will only consider the 16 voltage because the negative is not there. It is 0 voltage only. Now 0 voltage, all 0 zeros are equivalent to 0 voltage. All 111s is equal to 16 voltage. 16. How we are calculating this? So if the bit 0, bit 1, bit 2, bit 3 is our value in digital form, its equivalent to digital voltage is 16, that is V reference, multiplied by B3 divided by 2 plus B3 divided by 4 plus B2 divided by 4, B1 divided by 8, B0 divided by 16. If you will just check it for 1, 1, 1, 1, 1, 16 value. So just 1 by 2, 1 by 4, and then 1 by 8, 1 by 16. This will give you the value 16. So this is one thing to understand. Now we'll go ahead. Suppose this is our input voltage and the input voltage is 11.2 voltage. That is the analog value. The analog value is 11.2 voltage. That is voltage in. So this is voltage in. Here it is 16 volt. Here it is 0 volt. Now the first approximation would be, we will make this as 1, 0, 0. So whatever be our voltage reference, we'll just divide it by 2. So 1, 0, 0, if you will calculate it using this formula, you will get the value 8 voltage. It is just the half of the value. Now whatever be the voltage input, we require one comparator circuit which will compare the voltage in with 8 voltage. 8 volt. Now this voltage in is greater than the 8 volt. So we will keep this one as it is, because in the final value, obviously we require 8 volt, means the addition of 8, because 11.2 is greater than 8 volt. So we require 8 volts. So we know this, that at least we require 8 volt to add. So 8 is for sure will be there in addition, which will club together and figure out the final added value, which would be near to 11.2 voltage. So here we are sure that 1 would be there. So we'll keep this 1. Then we will make this 1, 0, 0. This is the next approximation. This is the next approximation. So we are adding 8. Already we have compared it with 8. Now I will add 4 more. So 8 plus 4, that is 12 volt. Now 12 volt we will compare with voltage in, that is 11.2. For that we require the comparator circuit, which will compare this voltage with 12 volt. Now 12 volt is greater than voltage in, so we will not consider this because we can't accommodate 12 volt in our addition because 11.2 is less. So we will omit this one. So the next one will be 1. So the next approximation will be, we will keep this value. So okay, we will see. And this equivalent to value using this formula is 10 volt. Now once again we will compare. Okay, this is the 10 volt and our voltage in is greater than, so we will hold this value. So this is nice approximation. This is near to the approximation. Now further we will accommodate this last value also, 1 1, and its approximate value is 11 volt, which is highly close to the 11.2 value, but it is still less than the 11.2 value. So whatever we have considered this one, we will keep this value. And as it is the 4-bit approximation, so we will in our next run the value would be 1011, because we have to keep this value because 11 volt is less than 11.2 volt. So this is our approximate digital value. So in this way successive approximation algorithm function. So if it would be 12-bit, then instead of 4 it would be the 12-bit approximation, and then means the algorithm would be much more refined. The digital output would be much more refined. So this is all about the functioning of successive approximation algorithm. Our LPC module uses 12-bit successive approximation algorithm. Now this voltage reference. So in our case, 16 volt is equivalent to, proportional to all ones in 4 successive approximation register. So this is approximate to voltage reference, that is 16 volt. Now V out, we want to calculate the equivalent voltage. That would be approximate to whatever we will get out of the conversion in 12 bits or 4 bits. This is 4-bit approximation. So whatever we have received out of conversion after passing it through ADC module, so that is what we received in our approximation register, in the data register. So now it is very simple ratio proportion problem. Now we will simply take the ratio, then V out would be equal to voltage reference multiplied by whatever be the value we have received, we got in our data register, that value. Obviously this need to be converted into its digital, means its decimal value, and this also need to be converted into its decimal value. So we will get the voltage out, that would be the approximate value in digital form. This is in the digital form, but it's equivalent to digital output in voltage. So in this way we can convert the equivalent to approximate digital output to its digital voltage output. This is all about the theoretical aspect regarding ADC. In our next lecture, I will walk you through some of the program where we will see the working of ADC both in software control and burst or the hardware control mode. And the one program would be just to interface ADC module with controller, microcontroller, and whatever microcontroller will receive the equivalent digital output, it will display that to LCD. And the next one would be that we will use both ADC 4 and ADC 5, and whatever be the difference, that difference we will calculate in terms of voltage, and that display that difference we will display over the LCD module. So that's all about this lecture. We'll see you in the next lecture.